Hello, everybody. I'm Satya Mallick, and I'm going to talk about computer vision, machine learning, and artificial intelligence today. Now, when I tell people that I work in artificial intelligence, different people have very different opinions. Some people think that AI is a monster. So I decided to create a meme. So this is what the world thinks I do. This is what my mom thinks I do. She thinks that I'm connecting machines to humanity. This is what my friends and other computer scientists think what I do. And yes, there is a lot of money in AI. I'm not denying that. And no, he is not Benjamin Franklin. This is what I really do. So I work in artificial intelligence, computer vision, and machine learning, and we solve some real-world problems. We are nowhere close to general artificial intelligence. So let me just start this by saying that there are big opportunities, but AI is overhyped and underhyped at the same time. There are some problems we can solve really well, and there are some problems that are just out of reach right now. Just to give a little background about myself, I did my PhD from University of California, San Diego in 2006, and right after that, I started a company with my PhD advisor called Site Commerce. The goal of that company was to apply machine learning and computer vision to problems in the fashion and beauty industry. And in 2015, I co-founded a company called Big Vision LLC. It's a computer vision and machine learning consulting company. Now, some people know me through my blog called learnopncv.com. And in 2017, IBM's AI blog named me one of the top 30 most influential people on Twitter in the field of AI. And the blog has been covered by BBC, the Time magazine, Huffington Post, and the Register. That's enough about myself. Now let's get to the real topic. Now let me begin the talk by saying a quote by Victor Hugo. Nothing is as powerful as an idea whose time has come. The idea here is artificial intelligence, and the time is now. We are looking at a technological revolution that has not been seen before. Now, one of the leading researchers in the field, Professor Andrew Ng, calls AI the new electricity. What does that mean? Well, when electricity was invented, the first application was lighting, light bulbs. But then it went on to transform one industry after the other. We had electricity in agriculture, in manufacturing, in medicine, and now it permeates all aspects of our lives. So AI is the new electricity. Why? Because AI is going to transform transportation. It's already transforming financial technology. We see cameras for surveillance everywhere. And it is transforming agriculture, manufacturing, medicine. So we are looking at a technological revolution. Just to give you an idea, this is a slide from AI Index. They published this data, which shows that between 2013 and 2018, a span of 5 years, the number of jobs in the United States where AI talent was required went up by 5 times. 5 times in 5 years. That's incredible. And the market is also responding. You can see the enrollment in Stanford's AI course last year was 1,500 students. That's just incredible. In a single class, 1,500 students. And I also publish an online course in artificial intelligence, and last year, 600 students joined the course. So that's incredible. Now, because the field is growing at such a rapid rate, there's a lot of buzzwords going around. So let me first explain some of these buzzwords. What is artificial intelligence? In layman's term, whenever we teach machines to think like humans, those class of technologies are called artificial intelligence. That's it. There is no other technical definition. Now, the next thing is machine learning. What is machine learning and how is it different from artificial intelligence? When we try to solve AI problems using data, we call it machine learning. There are other ways AI problems can be solved, for example, by using rules. But that's not what machine learning is. Machine learning is when we use data to solve AI problems. Inside machine learning, we have a smaller subset of algorithms called deep learning. Now, deep learning is a specific way of solving problems where neural networks are used to solve AI problems. Why is it called deep? Well, traditional neural networks had 3 layers: the input layer, the output layer, and there was a hidden layer which represented an abstraction of the data. And scientists figured out that if you had more than one hidden layer, so if you had hundreds of hidden layers, you could teach a lot of things to machines. The teaching becomes very easy. So deep learning is essentially neural networks with more than one hidden layers. That's it. Now, there is computer vision. Computer vision is the collection of all the technologies that help us interpret images and videos. We help machines see using computer vision. But computer vision is not only AI. There are a whole bunch of algorithms that have nothing to do with artificial intelligence, and they are all called computer vision. There is obviously a huge overlap between machine learning, deep learning, artificial intelligence, and computer vision, but there are also a whole set of algorithms in computer vision that have nothing to do with AI. So AI has essentially 3 parts. One is computer vision. We want machines to see. The second is speech, where we want machines to listen. And finally, natural language processing, where we use text data. We do analysis on text data. We interpret text data. So those are the big 3 parts of artificial intelligence. Now, why computer vision? Well, because 30% of human brain is devoted to visual processing. And compare that to 8% for touch and 3% for hearing. Only 3% for hearing. And if you ask my wife, she would say that, for me, it's not even 3%. Now, another thing that is happening is that visual data is everywhere. We have, from the moment an infant is born, a kid is born, we put a baby camera looking at them. And baby cameras not only detect today whether the baby is sleeping or awake, they can even monitor heart rates. And then we have cell phone cameras, we have laptops, our cars have cameras, the drones that we are building are useless without cameras, and of course there are surveillance cameras everywhere. So there is an abundance of visual data, and this visual data is extremely cheap. These cameras are extremely inexpensive, and they are everywhere. So that's why we care so much about computer vision. Now, until now, I have given you a very high-level overview of what these things are. But let's dive into some very basic details of these fields. So we will start with what is an image. Well, if you look at an image, there are various ways of interpreting what an image is. The programmer's view is that image is multidimensional data. We have the red channel, the green channel, and the blue channel that corresponds to sampling of the visible spectrum. And we have these 3 layers, and these 3 layers together form the image. Now, if you take that image to an electrical engineer, they will say, no, this looks like 2-dimensional signal. So I'm going to use signal processing to solve my problems. That's a valid way. If you take it to computer scientists, they would say that, no, these pixels are like nodes in a graph, and the similarity between pixels is the connection between them. So we will use graph theory to solve various problems in computer vision. And so there are various problems which are solved using graph theory. And then there are mathematicians who think that this array of numbers, which we call an image, you can string them together and into one long vector. And just like 3 points, like 3 numbers, x, y, z, is a point in 3-dimensional space, this image, when you string it out into a long vector, can be thought as a point in multidimensional space. And when you have this kind of representation, a lot of mathematical tools become available for analyzing images, and we'll see that. So back to our big picture, let's explore this area, the intersection of computer vision and machine learning. And to understand one problem in that area, I'll pick something called image classification. The goal of image classification is to label a given image. So given an image, we want to label it as a cat, dog, or other. So you could have thousands of classes, but in this simple example, I've just chosen cat, dog, and other. That's all. So we begin by showing a lot of data to the algorithm. Now, we take several images of cats, and we know the label. We take several examples of dogs, and we know that they are dogs. And we take several examples of images that are neither cats nor dogs, and we just call them other. The first step of image classification is pre-processing. Every image is converted to a standard form. We sometimes rotate it, resize it, crop it, so that every image is 256 by 256, or whatever standard value you choose. Once we have done that, we convert this image to a feature vector. Now, as I had mentioned, that you can string all the pixel values together and make an image into a vector. But that's not a very good representation of an image. And we will come back to this point later. But the important point to note is that any image can be converted into a vector in multidimensional space. And once you have that, you can apply a learning algorithm to classify the image into cat, dog, and other. And let's look at example of a learning algorithm. And for that, I have chosen support vector machine because it is an easy one to understand. The reason I'm explaining this in some detail is to convince you that machine learning is not magic. It is very simple science that anybody can understand and anybody can learn. So in support vector machine, what you're looking at are 2 classes of data. So the blue dots could be cats, and the red dots could be dogs. And for simplicity, we are looking at 2-dimensional data. So our image data is multidimensional, but for simplicity, in this example, we are looking at 2-dimensional data. Now, we want to build a classifier that is able to tell whether a point is blue or red. The easy way to do in support vector machine is to find a plane or a line in 2D that divides the space so that on one side we have one class and on the other side we have the other class. And now you may be thinking that, oh, you built a very simple, you picked a very simple example. What happens when the examples are complex? And the thing is that mathematicians are genius. I mean, they can cook up anything. For example, if you look at this data, you cannot separate this data using a single plane or a single line because it is circular. One is encompassing the other. So what do? You cook up a third dimension. So you apply this z to the data. So you take the x and y coordinates and create a mapping. You create a third dimension. And in the third dimension, you can see that the data is separable using a plane. So that's the plane that separates the red dots with the blue dots. And that plane actually corresponds to this circle. Now you can see that something that was very complex, how do you classify cats and dogs, is now very simple. They are just points in multidimensional space, and you are using planes to separate the 2 classes. And if the two classes are not separable by a plane, then you use a kernel to cook up some dimensions, and in that dimensions, hopefully, you can separate the data using a plane. And that's it. Now, the thing that is missing here is what kind of features are useful. So I mentioned that just taking the RGB values and stringing them into a long vector, you can do that, but it's not a good feature. So what makes a good feature vector? Well, there are a few characteristics. First thing is that when you convert an image to a vector, all the images of the same class, they should cluster together. They should cluster together in this multidimensional space. The other point is that if you take a different class, the different class should also cluster together. But these two classes should be separate. So you have two classes, they both cluster among themselves, but they are separate from each other. That is the kind of feature vector we want. And there is also something that we should not overwhelm the system. We want to reduce as much information and give the system only the necessary information. So in this case, if you look at this edge image, you can see that it is a person running. You cannot tell who is running, but you can clearly say that a person is running. So this image is enough. This is enough information for a machine learning algorithm to classify. And if you look at the original image from which it was derived, you can see that there is a lot of extra information that we don't need. Like, for example, the yellow jersey is irrelevant to classifying that it's a running person. So that's the beauty of a feature vector. It removes extra information, only preserves the necessary information, and in addition to that, it creates a space in which images belonging to the same class cluster together, and images belonging to different classes are separate. Now, there was a problem with this approach. The problem was that we were hand-creating these features. So if you wanted to work on face detection, you used certain kind of features called hard features. If you wanted to solve pedestrian detection, you used a different kind of features. So it was kind of a black art. You had to do a lot of experiments to figure out which features worked for what problems. And this became a problem because every time a new problem came in, you had to either invent a new feature, or you had to work with existing features. They may or may not work well. So as a result of this, we came up with several features. There is Sift, Surf, Orb, Brief, Hog. These are just names of features. And this is not even the complete list. So the idea then was, shouldn't we be learning these features directly from the data? Why are we handcrafting these features? So the idea was learning from data is better than designing features by hand. And for that, we need to go into deep learning. We go into this intersection of computer vision and deep learning. Now, to give you a 30,000 feet view of neural networks, it solves the same image classification problem, but you can think about it as a black box that contains both the feature detector as well as the classifier. So the two parts, the feature vector as well as the classifier, it is all in this black box. And we are not telling which features to use. It has a huge collection of features which are represented using these knobs. Just think about dials. And it picks the right features based on the data. When these dials are in the right position, it gives the right answer more often. And if it is not in the right direction, if these dials are not in the right spot, then it will give wrong answer. So how do you train a neural network? You train it in a very similar way as we train little kids. What we do is suppose you want to train a little kid on how to recognize balls. So you show them one ball which is orange, another ball which is blue. Some balls have texture, some balls have different sizes. And once they have seen enough examples, they know that it is not the texture or the color of the ball. It is the shape of the ball that says it's a ball. And then you take an egg and show it to them and ask, what is it? And they respond, it's a ball. And then you say, no, it's not a ball, it's an egg. And then you show different eggs to the kid. And finally, the kid is able to distinguish between what is a ball and what is an egg. And the process is exactly the same for neural networks as well. If you want to show it, if you want to build a classifier for cats and dogs, you show it examples of cats, and you show it examples of dogs, and then you show examples of things which are not cats and dogs, so that it learns different weights. So the way it works is, during the training process, you show the neural network an image of a cat. And based on some dial settings, the weight settings, it will respond, it will give you an answer. And if the answer is correct, then you keep the dial setting. If the answer is not correct, you go and fix the dial setting so that the answer becomes correct. Now, there's a principled way of doing it, but that's essentially what is happening. The principled way of doing it is called an algorithm called backpropagation, but essentially, you're able to show it images, and when it makes a mistake, the backpropagation algorithm is able to fix the weights, and now you suddenly start getting good results. Okay, so that was a very high-level view of neural networks and deep learning. Now, we are in the third part. Let's explore this part of computer vision that has nothing to do with machine learning or artificial intelligence. And we will have a lot of fun doing this. These are two unpopular people in the United States. So let's have some fun at their expense. Let's swap their faces, like that. Now, I'm going to show you that this is actually not very difficult at all. This is actually very simple to do once you know a very few principles on how to do it. The first thing actually involves machine learning. The first step to do something like this is called facial landmark detector. So given a face, you're able to figure out where the landmarks are. So there are 68 points in this feature detector. It was trained on a few thousand images, and now it is able to detect, given a face, where these landmarks are located. And in machine learning, these kinds of problems are called regression problems. We have two different kinds of problems in machine learning. One are called classification problem that we saw earlier, where the objective is to assign a label to the input data. So you input a cat, and the answer should be a cat. So it's a labeling problem. The other kind of problem is a regression problem. You input data, and the output is a number or a collection of numbers. So this kind of problems are called regression problems, and facial landmark detector is actually a regression problem. Now, once we have detected the landmarks on one face, we do it on the other face as well, then we are not interested in all the points which are inside the face. For this particular application, we can actually remove all the points that were inside using an algorithm called convex hull. It is just a boundary detection algorithm. It finds the outside boundary of the shape. Once we have done that, we do something called Delaunay triangulation. Now, Delaunay triangulation takes a collection of points and triangulates them so that the space between them is spanned by a collection of non-overlapping triangles. We will see in the next slide why this is important. Now, we can do the same thing for the second image. So we have two images. We have done facial landmark detection on it. We calculated the convex hull to find boundary, and using those boundary points, we have figured out, we have done Delaunay triangulation on both of them. After that, suppose we were able to transform one triangle to another, then we can transform each triangle in the left image to one triangle in the right image, and we will solve the problem. So you can actually transform one triangle at a time and transform the left image onto the right image. Now, triangle-to-triangle mapping is something called an affine transform in computer vision. It's very easy to calculate. Any triangle can be mapped to any other triangle. And all you need is the points, the 3 coordinates of the triangle, and the 3 coordinates of this triangle. You can find a 3x3 transform that transforms one triangle onto the other. And once you have found that transform, you can apply it to all the pixels inside that triangle and transform all the triangles, all the points inside the triangle onto the other image. And the end result is something like this. So you're able to transform one face on top of the other. The problem is that it doesn't look pretty. You can see that the 2 images were taken under 2 different lighting conditions, and so you can see the seams of when we do this transformation. Fortunately, we have another algorithm that solves the seam problem. It's called seamless cloning. And in this application, we usually have a source image and a destination image. The source image is applied onto the destination image. Now here, it's a naive application. You can see we wanted to put the airplane in the scene, but doesn't look good because it has a boundary. If you give it to a Photoshop artist, they will be able to remove the boundary, and you get something like this. But it is still not attractive because the lighting has not been fixed. And fixing the lighting problem, it's tedious. Removing the background is also tedious, but fixing the lighting is also tedious. So it cannot be automated easily using Photoshop kind of application. So we do something called seamless cloning, where the objective is to match the lighting as well as blend it seamlessly. And the way to do it is to blend the images in gradient domain. So you must have, in high school, you must have read about derivatives. So a function, you take the derivative of the function. It is just, the difference operator in 1D. In 2D, you still have the difference operator. In gradient domain, you get rid of lighting effects because you are taking differences. You get rid of lighting effects, and then you can merge these images in the gradient domain and reintegrate the image to create this beautiful looking image called a seamless cloned image. So even though the math behind this is slightly involved, in OpenCV, the library that I used, it is just 1 line of code. So you can see that if you know what to do, even though you don't completely understand the mathematics behind it, there are a lot of applications you can build. So we apply seamless cloning to our algorithm. We have the source image, we have the destination image, we create a mask, and then we seamless clone using the mask. And you can see the output image, which is on the extreme right. Now, the techniques that I have shown until now, they can also be used for other applications. For example, face morphing. So the techniques that I have shown until now, exactly, you can combine them in different ways and create this application called face morphing. Let's see if it... And suddenly you have morphed Hillary Clinton into a tiger and back and forth. So with a few simple rules, a few simple algorithms, you're able to do some very interesting things. And the seamless cloning example that I had shown, or the face swapping example that I had shown, people have made apps worth millions of dollars using just 200 lines of code. So you can see that once you learn a few things, you can combine them in different ways to create interesting stuff. Here's another example. Exactly same technology, the things that I mentioned, affine transform, and then some amount of blending, and it creates this average face. And here, you're looking at many different precedents and the average face constructed using those images. And this example was reconstructed using all the things that I mentioned right now. That's it, maybe 50 lines of code. Now, I want to end this talk by saying that you guys are in an excellent position. You picked Perl as the language of expression, you used Python as the language of expression and not some other language like Perl, which is write-only. So the beauty is that AI, the language of AI today is Python. So if you want to enter this field, it's a good start to have a working knowledge of Python. So all the different platforms right now, they support Python. So OpenCV, which is a computer vision library, it has Python bindings. TensorFlow, Keras, Caffe, PyTorch, these are Python libraries for deep learning. And of course, many of you may already know scikit-learn. So make the best out of this advantage you have. If you're interested in AI, this is the time to join the revolution. So that brings me to the end of this presentation. I hope I'm able to convince you that if you're interested, you should join this AI revolution. Big things are happening. Right now, as you know, engineers are required to know programming at this point of time. And very soon, maybe in 2-3 years, engineers would be required to know artificial intelligence. It is a very big field. It is a revolution in the making. Join the revolution. Thank you. For beginners, we do have an online course. You can go to cvforfaces.com. We also have a coupon code for PyCon specifically, called PyCon. And we open it for enrollment specifically for PyCon, and the enrollment closes when the conference closes, February 11th. So if you're interested, please go there, check it out. I'm ready to take questions now. Yeah, go ahead.
You mentioned a number of machine learning tools, for example, Keras versus TensorFlow. Do you have any preference between the two?
So when you're a beginner, if you're a beginner yeah, so let me repeat the question. The question is that I mentioned a lot of deep learning tools, Keras, TensorFlow, PyTorch, Caffe. Is there a preference? So we, in our consulting work, we used to use Caffe. That was the most popular one. And now TensorFlow is by far the most popular one. And why do you care about popularity? First of all, TensorFlow is backed by Google. So it is almost 3 times or 4 times, the adoption is 3 or 4 times that of any other tool. The closest one is Keras. The beauty of Keras is that it's very easy. TensorFlow is a little bit hard to learn in the beginning, but once you get a hang for it, then it becomes easy. But Keras, it is designed for ease. So it is very easy to pick up Keras. So if you're a beginner, it is okay to use Keras, but as you go to more advanced level, you may have to work with TensorFlow, because a lot of cutting-edge research, they release their code in TensorFlow these days. You want to use, you want to take the benefit of that open source code they have. Yeah, go ahead. So the question is how important it is to have a master's or a PhD to enter the field of AI. The best thing that has happened in the last few years is that nobody cares about certification anymore. What people care about are your skills. Now, if you create something cool, put it on GitHub, if that gets traction, you don't need a master's or a PhD, but you need the right skills. So master's and PhD, when I'm hiring for my company, I actually do not look at whether they have a master's or a PhD. I look at whether they have the right skills. And that's true about a lot of other companies also. And there are a lot of good deep learning courses by top people in the field. So one of the course is deeplearning.ai, which is the best deep learning course right now. And it's by the best people in the world. So if you get that certification, you have completed that course. I don't think anybody cares whether you have a master's or not. And there is another one called self-driving nano degree on Udacity. That is also taught by the top people in the field. And you cannot actually, there doesn't exist another degree course like that. The self-driving nanodegree, you cannot find it in universities. That is the quality of that course. So if you do online courses, the right ones, you can have the necessary skills to enter the field. Yeah. Go ahead. So the question is, how many months do you need to invest to be a good AI developer? Now, if you look at deep learning, then deep learning, a lot of problems in deep learning can be solved if you know two problems, how to solve two different problems. One is image classification, the other is object detection. If you know how to solve these two problems, then you have a very solid footing. And my guess is that with 6 months of good reading, you can be up to par with the state of the art in both those areas. And the advantage we have today is that a lot of code is public. So if you are stuck somewhere, you can easily try out publicly available code. And this is not code which is suboptimal. This is code that Google, Facebook are actually using in their production. They won't share the exact model, but they would share the architecture. So I would say if you're ready to commit 6 months of your life to AI with some mathematical background, you should be able to pick it up. And when you're trying to classify cats and dogs, the classes are very different. But suppose you want to do face recognition, what kind of algorithms do you use? How do you use deep learning? Is that correct? Yeah. So for face recognition, so you still use the same kinds of features for face recognition also. Only the objective function changes. So in case of cats and dogs, the objective function is to divide this into cats and dogs. In case of face recognition, they build a space, a metric space, where each face, so your face would form a different cluster than somebody else's face. And when you change the objective function, you are able to do that. And once you get a new face, when you enroll a new face, all you have to do is find which is the closest cluster. So the class of techniques is the same. The objective function is usually different. What you're trying to optimize is different. In one case, you were trying to cluster cats and dogs, but here it's a specific human being. It's a more challenging problem, but it is only about changing the objective function, usually. Yeah, go ahead.
I see I see that you speak a lot about deep learning, but what about what kind of other techniques are being used in the industry right now? Only deep learning, or? Okay, I see that you speak a lot about deep learning, right? But I want to know if you know what other techniques are being used in the industry right now, different than deep learning.
So in the industry right now, deep learning is dominating. Just to give you an example how dominant the class of techniques is, in 2010, they started an image classification competition. And as far as I can remember, the top prize was something like 71, 72%. In 2011, that number went up by 2%, so 72, 74% or something like that. In 2012, deep learning-based solution won the first prize. It was 85%. So we were making these incremental progress, 2%, 3%, and deep learning arrived, and it was at 85%. The second prize was 76%. In 2013, all winning entries were deep learning based. In 2015, that specific competition was canceled because deep learning exceeded human level classification. And not just one algorithm, I think 3 algorithms surpassed human level accuracy. So even for somebody who has been in the field for a long time, I literally fell off my chair when I first tried using deep learning in my business, and I was convinced that I was doing something wrong. My my error rate was 95%, sorry, not the error rate, my accuracy was 95%, and I kept checking my architecture, my code, to see that I probably made a mistake somewhere. It cannot be that high. So the question is that because of his background as a systems engineer, we can use, for deep learning and other machine learning applications, we have a lot of libraries. We can use them and solve real-world problems. But if you want to dig deeper, then do you have the tools, the mathematical tools, to actually enter the field? My answer to that is yes, it does require a little bit of mathematics. And if you look at the entire machine learning literature, then you need to have a background in statistics. But if you look at deep learning, only deep learning, it consists of high school mathematics. You need to know the chain rule in calculus to at least understand the basics. Like the most popular algorithm, backpropagation, is nothing but chain rule applied recursively. So there are parts of machine learning which are new, and very simple things work in those areas. So yes, if you want to publish a paper in a top conference, you will need that kind of knowledge. You will need to build that knowledge in statistics and machine learning. But if you want to apply it to real world, it doesn't need that much. Yeah, go ahead.
Okay. Mr. Satya, welcome to Medellin. What is the better notion for repository of backend for deep learning, artificial intelligence? Windows Azure, Google Cloud, or Amazon WS? What is the better option for repository of backend for deep learning and other resource intelligence, artificial intelligence, like Windows Azure, Google Cloud, or Amazon WS? Thank you.
So the question is, as a backend, what infrastructure should you use? Should you use AWS or Microsoft Azure, or should you use Google Cloud? I personally do not have experience with Azure, but we use, in our business, we use AWS, and that has worked out beautifully. They not only came up with the first GPUs on the cloud, but once you are in their system, everything works seamlessly. So I do not have enough experience with Google Cloud to say which one is better. But what I can say is that AWS has worked beautifully for us. Yeah, yeah, go ahead.
Basically, my question is, in your consulting experience, did you have the opportunity to mix computer vision with reinforcement learning? And in case yes, if you are not limited by any NDA, can you comment of us? Yeah, okay. My question is, in your consulting experience, did you have the opportunity to combine knowledge from computer vision with reinforcement learning? And in case yes, if you are not limited by any NDA, can you comment on that?
So, like I was saying before, that we have never had to use reinforcement learning in the consulting work. We do use it for, to do our own experiments and to figure out stuff, but a lot of consulting work boils down to image classification, object detection. So you use the state of the art in these two things, and you're pretty much good. So most of the problems that we solve are in these two categories. And there are different, I'll give you a flavor of how these things are slightly different, but they are all very similar. So one of the consulting works that we did was in face recognition, and the other one was trying to figure out fakes in fashion merchandise. So you could have some fashion products which are very expensive, and you want to figure out whether it is fake or real. So on one end, we are doing fashion, high-end fashion work. On the other hand, we are also analyzing horse feces, the stool of horse, to figure out whether the horse is sick or not. So we are detecting parasites in that. So that becomes an object detection because we are detecting specific parasites. So you can see that even though the flavor of this object detection and image classification problems are very different, they are essentially the same class of problems. And that's why I say that if you want to enter the field as a problem solver, the amount of literature that you need to read is really small. Something like 100 papers would make you a solid expert in the field, in the practical aspects of the field. Yeah, go ahead.
Hi. So it seems to me like deep learning is like the easiest and most accurate solution right now. Is there any reason not to use it, to use something else?
Yes. So there are a few cases where deploying deep learning solution may be slightly tricky. So the alternative to deep learning can sometimes be using feature vector like hog features and then a machine learning algorithm like SVM. So you can solve image classification using hog plus SVM, and that has you have that implementation in OpenCV, which is a very popular computer vision library. And suppose a client already has OpenCV on their system, then it is just easier for us to use that, and if it gives good results, if the problem is simple enough, it gives good results, then you don't need the deep learning infrastructure to come along. Although now in OpenCV also you can import models, deep learning models for classification. But usually, for most of the problems, for most of the cases, deep learning ends up being the best solution. The accuracy level is so high that you just use that.
Okay, we have time for a last question, so.
At the very beginning of the speech, you talked about artificial intelligence, but not specifically machine learning or deep learning. What are those tools that exist to apply the artificial intelligence based on rules and not on deep learning or machine learning?
Are you asking what are examples of artificial intelligence based on rules?
Examples and tools to
So,
that.
so the reason I mentioned that was because when it started, artificial intelligence started as a field, it was not clear what approaches to use. One example of, let's say you want to detect, so it's not very popular to not use data. It's not very popular to not use data, but often we encounter a problem where we do not have enough data. For example, suppose you want to detect or you want to find buttons, shirt buttons which is lying on a table. And you do not have enough examples of that and you do not want to spend the time, then you would simply do something very simple. You would use edge detection to detect edges, and then you would use something called Huff transform to detect circles, and then that would be your location of the button. In that case, we did not use data, but we still solved the problem of finding the button. But if you have the data, those solutions are not popular. And so each of that solution has, because it is rule-based, you have to come up with the rules. So that's a challenge. Any other question? Yeah, go ahead.
Gracias. Good morning, everyone. How does I don't know how to explain this, but how does your program or any face detection makes a difference between a real face and a picture of a face? Are you working on this, or how can I make the difference not to cheat the artificial detection of faces?
That's a very good question. The question is, how does an algorithm know whether it's a real face or a photograph of a person? So in 2 dimensions, if you're looking at just 2-dimensional data, it's very difficult to make that work. So the way people try to figure out is through a video. So in a video, they would ask you to do certain things. And if you do those things, it's like a password. So you're blinking your eye or something like that. That's one detection of liveness. In iPhone, for example, they use a pattern, they project a pattern onto the face, and then they recognize the 3D structure of the face. You can still fake it using a fake mask. So there is always a way to fake these things, but it's challenging to do it on a single image. There are other small techniques, like we did it for a client where they were interested in finding when somebody's taking a picture of a screen. Fortunately, that problem is very easily solvable because screen has a specific pattern and it can be recognized. When you take a picture of a screen, you can see that pattern. You zoom into the image, you can see that pattern, and you can train a classifier to say that it is real or fake photo. So there are different techniques based on how much hardware is available to you. But with a single image, it is a difficult problem. I don't know whether you can see this. Can you see my face there with a beard? And maybe it's not clear. That was a demo of real-time face swapping. And it's not very visible here, but I was trying to swap my face with Juanes, the singer, his face. OK. So that is it. Thank you.